Hi there. Today we're going to be continuing lesson 2-4 on the chain rule, but this time we're going to be adding the excitement of trig functions along with it. So here are the chain rule versions of the trig functions. Obviously, and again, u is some other function, like something like more sophisticated than just x, okay? So you could be like 5x, you could be like 3x squared minus 8. You could be 4x over 3x squared minus 2. I don't know. You know what I mean? But so u is going to be a different kind of function. So remember, using the chain rule, that means we'd want to take the derivative of sine of u. So that's the cosine of u. And then we're going to take the derivative of the inside function. And that's really what all of these explain. Okay, that we're going to take the derivative of the trig function with u, but then take the derivative of u, of that inside function. So let's find the first derivative of these questions in example 4. We have y equals the sine of 2x. Before, when we had a problem like this, we had to use the double angle formula to deal with it. But now that we know the chain rule, we don't have to use that anymore. So let's see what we can do to find y equals sine of 2x. So again, the inside function is going to be the 2x, and then the whole big function is going to be the sine of 2x. All right, so that means that if I want my y prime, I want the derivative of the sine of 2x, so that's going to be the cosine of 2x. And now I want the derivative of the inside function of 2x. So that means I'm going to have cosine of 2x times, well, the derivative of 2x is 2. So that tells me that my derivative, you probably would write that as 2 times the cosine of 2x. So I want to go back and show you what we had to do before. Remember, this was back in, I think this was 2-3, where we had the sine of 2 theta, and we couldn't do the 2 theta yet, so we had to rewrite it as a double angle, using the double angle formula, and then we had to use the product rule. You can see that now that we know the chain rule, that makes this a lot easier to do, doesn't it? So that's pretty exciting. Let's try letter B. We have the cosine, y equals the cosine of x minus 1. Well, if we want to differentiate, maybe we'll mix this one up and call this dy dx instead of y prime. All right. We want the derivative of cosine of x minus 1. So we're going to apply the rule there. Remember, the derivative of cosine is the opposite of sine. So I'm going to have the opposite of sine of x minus 1. But now I need to be safe and take the derivative of x minus 1. So that gives me the opposite of sine of x minus 1. And the derivative of x minus 1 is 1. And so that means that our derivative is just the opposite of the sine of x minus 1. And that's the derivative. Oh, I didn't happy cloud this one because I got excited. Okay. Letter C, I've got y equals the tangent of 3x. Again, 3x is more sophisticated than just x, right? So we're going to have to apply the chain rule. So if I'm going to do the derivative, I want the derivative of tangent. And when I take the derivative of tangent, that's secant squared. And I'm going to keep the input secant squared of 3x. But now I want to multiply that by the derivative of that inside function. So that means that I have secant squared 3x. I probably should put that in parentheses. Times 3, since 3 is the derivative of 3x. And so if I were to write my final answer, I would pop the 3 up front. So I have 3 times the secant squared of 3x. Even without the parentheses, it's understood that that's there, okay? If you want to put them, you can be safe. But that would be a nice way to write that derivative. How about letter D? F of t equals the basically sine of 4t all cubed. Okay, so sine cubed 4t. And the basic function, like the big function, is something cubed, right? So we have something that's being cubed here. So that's going to be my outside function, is this whole piece here. So if I want f prime of t, I'm going to need to take the derivative of this, so that's going to be 3 times the sine of 4t squared, right? So sine squared 4t. But now I want the derivative of sine of 4t. Okay, that's what we were cubing, right? This was the sine of 4t all cubed. So that means that our inside function wasn't 4t, it was the sine of 4t in that piece there. So again, I have this 3 sine squared 4t, and now I want to take the derivative of the sine of 4t. Well, here's the thing, there's an inside function there. The outside function is this idea, the sine of 4t. So let's take the derivative of sine, which is cosine. But then now we need to take the derivative of this inside function, which is 4t. So this is the function in a function in a function type of a thing, okay? So then I have 3 times the sine squared of 4t times the cosine of 4t times the derivative of 4t, which is just 4. And then I can multiply all those things together. I'll multiply the 3 and 4 together, maybe to make 12. Sine squared 4t times cosine of 4t. Okay, and if you want to do this, you can, whatever. Okay, we're good. But that would be our derivative there. Okay, so 12 times the sine of 4t all squared times the cosine of 4t. Okay. So let's look at some other ones, and let's find the derivative of these trig functions. The first one is the cosine of 3x squared as our y value. Notice that our inside function is 3x squared, and our big outside function is the cosine function. So if I wanted to find y prime, I need to take the derivative. I hope I haven't been saying inverse this whole time. Take the derivative of cosine, which is the opposite of sine, of 3x squared. But now I need the derivative of the inside function. I need the derivative of 3x squared. So I still have the opposite of the sine of 3x squared, but now I need to take the derivative of 3x squared. And the derivative of 3x squared is 6x. And we look good here. So that means that my y prime is going to be negative 6x times the sine of 3x squared. Okay. In letter B, we have the cosine of 3 times x squared. Well, you guys, this is a constant, isn't it? That's just a constant multiplier. That's not a function itself. If it was the cosine of x, that would be one thing. But this is the cosine of a number. That's just a constant. So that means that's going to be a constant multiplier. So I'm just going to keep the cosine of 3, and then as the constant, pull that out, and now take the derivative of x squared, which I know is just 2x. And so, I don't know, I guess you could leave it like that, or you could write 2x times the cosine of 3, or 2 times the cosine of 3x. I would be careful writing it as the cosine of 3x, you know what I mean? Anyway, so those are some ways that you could write that in letter B. In letter C, I have y equals the cosine of the quantity 3x squared. So you could think about this as a function in a function in a function, like where the outside function is cosine theta. The inside function is 3x squared, or sorry, u squared, and then the inside function would be 3x. But I would, in this case, instead, I would simplify this. I would write this as the cosine of 9x squared. So remember, when the squared is here, we're not squaring the cosine, we're squaring like the argument of the trig function. So this is really like the cosine of 9x squared. And when we have it like that, now we just have one big outside function of cosine of u, and then the inside function is just 9x squared. So our outside function, we can take the derivative of the left to get y squared, and we take the derivative of the right. The derivative of cosine is the opposite of sine. So I have the opposite of sine 9x squared. But now I want to take the derivative of that 9x squared. So I have the opposite of the sine of 9x squared. And I know that the derivative of 9x squared is 18x. And now it looks like I've gotten everything taken care of that I need. So my y prime is going to be negative 18x times the sine of 9x squared. Okay. Now in letter D, this squared is saying that it's cosine of x that's being squared. So my outside function is like u squared, and the inside function is cosine of x. Okay. So again, maybe you want to think about this. If it helps you to write it like this, that's fine. Okay. That's really like the cosine of x squared, which means that this idea of u squared is going to be the outside function. Okay. So that means that if I were to take the derivative, that means that I would want to do 2 times the cosine of x to the first power, right? Because I take one away. But now I want the derivative of the inside function, which is cosine of x. So I still have this 2 times the cosine of x, but now I want the derivative of the cosine of x, which we know is the opposite of sine of x. And now that I've taken the derivative of everything, I can just turn that into negative 2 cosine x sine of x. Wait a minute. That's something that's familiar, isn't it? If we have 2 sine x cosine x, or because of the commutative property, 2 cosine x sine of x, can't we use the double angle formula? Isn't this the same as, oops, no 2 in front. Isn't this the same as the sine of 2x? But we have to make it negative, and that would be a way for me to write my y prime is the opposite of the sine of 2x. So again, here I can use my double angle formula. Oh my goodness, okay. So notice that the placement of the square and the parentheses make a big difference, okay? In something like letter A, it was just the x part of the argument that was being squared. Whereas in C, it was the whole argument 3x that was being squared. Where in letter D, it was the cosine function that was being squared. And in letter B, this set of parentheses meant that that was just a constant instead. So just be really cautious about where your parentheses are, where the exponents are when you're doing your derivatives. Okay? Okay. All right. Example 6. Find all points on the graph of f of x equals the cube root of the quantity x squared minus 1 squared, for which f prime of x is 0, and the points where f prime of x does not exist. Well, since we're dealing with f prime of x, we're going to have to find the derivative. So maybe we could make this into something that doesn't look quite so obnoxious. Remember, we can rewrite this using rational exponents. That's going to give us x squared minus 1 to the 2/3. And now we can use the general power rule, which involves the chain rule, to help us out a little bit. So the f prime of x is going to be the derivative of this whole piece. So that's going to be 2/3 times x squared minus 1 to the negative 1/3. And then times the derivative of that inside function, x squared minus 1. So that gives me 2/3 times x squared minus 1 to the negative 1/3, and then times 2x. So let's maybe clean that up by getting rid of the negative exponents, multiplying them together, etc. So my numerator would have 4x, and my denominator would have 3 times x squared minus 1 to the 1/3. You could write it like that. Or sometimes if that's going to be the final answer, I don't know, I think it looks nicer with the cube root instead, okay? So there's f prime of x. I guess I shouldn't have happy clouded. That's just an interim step. So now what we want to do is we want to find the times when f prime of x equals 0. So let's look at those times when x prime of x is 0. That means that we want 4x over 3 times the cube root of x squared minus 1 to be 0. Well, pretty easily we can see that 4x is going to be 0, x is going to be 0. So we know that at x equals 0, f prime of x would be 0. Well, it wanted us to find the point on the graph. So again, let's find this point on the original graph. And that means I need to find f of 0, right? So f of 0 is going to be the cube root of 0 squared minus 1 squared. So that's going to be the cube root of negative 1 squared. That's the cube root of 1. And so that means that f of 0 is 1. So maybe I'll put that here, that f prime of x equals 0 at the point 0, 1. So that's the answer to one of the pieces. It wanted the point, sorry, they wanted the point where f prime of x was 0. So f prime of x is 0 at x equals 0. And so on the original graph, that point occurred at 0, 1. Okay. Well, now it also asked about when f prime of x does not exist. So when wouldn't this exist? Well, f prime of x does not exist when the denominator equals 0, right? Because then we wouldn't be able to divide. So let's set 3 times the cube root of x squared minus 1 equal to 0. So if we do all the steps, I could multiply by 3. I know that doesn't do much. We can cube. I know that doesn't do much. And then we can solve, and we find that there are 2 points that would occur when x is 1 and when x is negative 1. Similarly, we're going to find these points on the original graph. So I need to find f of 1, and I need to find f of negative 1 then. So f of 1 is going to be the cube root of 1 squared minus 1 quantity squared. So that's going to be the cube root of 0 squared, which is 0. And f of -1 is going to be pretty similar, huh? So this is going to be -1 squared minus 1, that quantity squared. So 1 minus 1 is 0. So the cube root of 0 squared, which is again going to be 0. So those would be points where the graph is undefined. So f prime of x does not exist at 1, 0 and at -1, 0. And that would answer those questions. Okay. Alrighty. So that's pretty much it. This is just a summary down here of the basic derivative rules that we've talked about so far. I think we've mastered the constant multiple rule. We utilize the sum difference rule all the time. We're coming into our own with the chain rule, especially when and the product and quotient rule as we practice that within the chain rule. And then these are the basic derivatives using the power rule of the 6 trig functions. And the only two you guys don't know are these two down here. You guys will just learn those next year. We're just not going to touch on those right now. But those are some basic ones that you guys will learn next year. Okay? Well, that is it for our lesson 2-4. Hopefully, you guys are getting better at this idea of the chain rule. Again, remember, anytime that the inside is something other than just plain x, you've got to take the derivative of that special function as well. Okay? All right, that's all. You guys take care. We'll see you in 2-5 with implicit differentiation. Get excited.